Have you ever thought of traveling in space to places where even light takes years to reach? That's why some units of distance are also known as light years. Even if we make a plan to visit the Proxima Centauri, the nearest star to our solar system, traveling at a speed of 148 km per second, which is the speed of fastest man-made spacecraft, we would not even be able to cover a minute fraction of the distance in our whole lifetime. But there can be another way: wormholes. A wormhole is like a hypothetical tunnel that can connect two different points at extremely long distances such as billions of light years or more. But how can these hypothetical wormholes be formed? As pointed out by Einstein and earlier by his teacher Minkowski, we live in a four-dimensional world. It is the fusion of three spatial and one time coordinate. These together make the spacetime. For simplicity, one can think of it as a trampoline, as the spacetime is also flexible and bends around mass. Now imagine if we place two extremely dense and compact objects at two different locations in the spacetime. The gravitational force of those objects should be strong enough that allows bending in spacetime to such an extent that objects touch, and at that instant a wormhole is formed. Such formed wormholes will allow us to travel in both the directions and are known as traversable wormholes. These wormholes are unstable and tend to collapse quickly because gravity around them tries to close them down. To make a wormhole stable, we need something called as exotic matter. The properties of the exotic matter are much different from the properties of the known matter. Exotic matter is something that has negative mass. As positive masses attract each other, a negative and a positive mass will repel. So exotic matter will act as an anti-gravity that will keep our wormhole open. The traversable wormhole that is held open by exotic matter is also referred to as MORRIS-THORNE wormhole, and such wormholes are stable. These kind of wormholes are our best bet for space travel and for time travel too. As MORRIS-THORNE wormholes connect two different places in space-time, in addition to space travel, they could also be used for time travel. But it is not that simple. For this, one end of the wormhole should be traveling in space at a reasonable fraction of the speed of light. As for the observer of the traveling end, time will be moving significantly slower, as the speed of that end is at a good fraction of the speed of light, than for his counterpart which is observing the static end. To understand this, imagine that you are traveling at the speed of light. While traveling, if at any instant you will look at your watch, the time seems to be freezed. This is due to your high speed. Now if we travel through moving end of the wormhole and exit through the static end, we would be time traveling to the future, since the moving end is experiencing time at much slower rate than the static one. But can theoretical travel through wormholes become a reality? The main problem in our way is of exotic matter. To make a wormhole stable, we would be requiring an enormous amount of exotic matter. We not only have to make it stable, but also need to increase the size of the wormhole so that our spaceships can actually go through them. However, the exotic matter has only been observed in very small amount, not nearly enough to hold open a wormhole. Unfortunately, we have not yet observed a stable wormhole as shown in movies, where travel through space and time is unchallenging. But let us hope that a day comes soon when we travel to Proxima Centauri to unveil some of its secrets too.